Make sure it's working. Okay, it seems that it is working. So it's my pleasure to introduce Lisa, who's going to talk today about a Lie group analog for the monster Lie algebra. So thanks, Lisa.
Thanks very much for the invitation. It's a great pleasure to be here, and it's nice to meet everyone. So today's talk is going to be about the following picture and generalizing this picture to infinite dimensions. So of course, as we all know very well, if we have a finite dimensional simple Lie algebra, it has an associated simple Lie group, which we can also think about as a linear algebraic group. And for example, of course, if SL2 is a Lie algebra of 2 by 2 matrices of trace 0, then its associated group is the group of 2 by 2 matrices of determinant 1. And in finite dimensions, the classification of simple Lie algebras is easy to state. There are these 4 infinite families and 5 exceptional examples, and they have corresponding linear algebraic groups. Now, really what we're going to focus on today is the relationship between the Lie algebra or the Lie group and its Lie algebra. In infinite dimensions, we see the picture in reverse. We start with a Lie algebra, and we're faced with the question of associating a Lie group or a Lie group analog. Now, in finite dimensions, the relationship is very special. Lie groups came first, and as a way of linearizing the Lie group multiplication, the brilliant idea of Sophus Lie was to take a tangent space at the identity element so that the Lie bracket is actually the linearization of the group multiplication, and the formal exponential map from the Lie algebra takes us back to the Lie group. But in finite dimensions, this has a very nice properties. Of course, we can go back by taking the formal derivative with respect to a variable and setting it equal to 0. And we then, in this way, go back from the Lie group to the Lie algebra. Now, in infinite dimensions, a lot of things are different. And let's just introduce a couple of classes of infinite dimensional Lie algebras. So firstly, Kac-Moody algebras are the most natural generalization to infinite dimensions of the finite dimensional simple Lie algebras. And then there's a further generalization of Kac-Moody algebras proposed by Borcherds, called Borcherds algebras or generalized Kac-Moody algebras, or in physics, they're called Borcherds Kac-Moody algebras. In many cases, these can be constructed from physical subspaces of vertex operator algebras, and particularly if we're coming at it from the point of view of conformal field theory, this is a natural approach. Now, for today, our primary example of an infinite dimensional Lie algebra is a Borcherds algebra known as the monster Lie algebra. And this admits an action of the monster finite simple group, as we'll see later on. Now, one of the things I've been interested in over the past years is associating groups to Kac-Moody algebras. And there's really an established theory by many, many authors using different techniques, in some cases, different additional external data. Now, it's natural to try to generalize this question of associating groups to Borcherds algebras, but we'll see that even the methods we use in the Kac-Moody case break down. And so today I'd like to talk a bit about some of the issues that arise and how we could get around them. Particularly the question of associating an analog of a Lie group to the monster Lie algebra. Now, what is the monster Lie algebra? Well, its existence, of course, is due to the existence of the monster finite simple group, which, as we know, is the largest sporadic group of a very, very large order with lots of primes occurring in the decomposition of the order. Now, M, the monster Lie algebra, was constructed by Borcherds as part of his proof of the Conway-Norton Monstrous Moonshine conjecture. He discovered the monster Lie algebra as an example of a whole new class of, well, he invented this whole new class of Lie algebras, which turned out to be related in different ways to physics, number theory, group theory, and representation theory. And in the initial discovery, the monster-Lie algebra can be defined as a quotient of the physical space of a certain vertex operator algebra. Now, it's a tensor product of two vertex operator algebras. V natural is the incredibly famous and important Moonshine module of Frenkel-Opowski and Merman, which is the vertex operator algebra whose automorphism group is the monster finite simple group. V11 is also a vertex operator algebra for an even unimodular two-dimensional Lorentzian lattice. Now, it turns out that the generalized Kac-Moody algebras or Borcherds algebras also, in many cases, they can be described, as we've just said, as quotients of physical spaces, vertex operator algebras, but they also have a realization in terms of generators and relations, where we start with, as I'm sure you know, if we start with a Cartan matrix in finite dimensions, we can write down the presentation of a Lie algebra in terms of generators and relations using the data from the Cartan matrix. Now, the same is true in the Kac-Moody case and also for Borcherds algebras. So we have a realization for the monster-Lie algebra in terms of generators and relations. So here now we start with an infinite generalized Cartan matrix. It's probably very different from things you've seen in the finite dimensional and Kac-Moody case. Well, first, it's infinite. Second, there are now allowed to be negative numbers on the diagonal. And in this particular matrix, the numbers occur in these blocks of finite but increasing size, labeled by these coefficients C of 1, C of 2, and so on. Now, these coefficients, the numbers C of j turn out to be coefficients of q in the modular j function. So this is well known. These numbers are famous. Of course, 196,884 is a well-known number, and so on. Now, to get the presentation of the monster-Lie algebra, we take the Lie algebra whose generators and relations are encoded in this matrix, and we mod it by the center. Now, essentially the same information can be encoded in a Dinkin diagram, which is also very special. Of course, it's an infinite diagram. It's got two types of roots. There's a single root, which is labeled alpha minus 1, which is different than all the others. And that's because it is what we call a real root, which I'll define in a moment. Then there's this infinite line of so-called imaginary simple roots, which I'll also define. But in general, this is a complete graph on a countable set, missing only one edge, namely between alpha minus 1 and alpha 1k. This graph also has multiplicities, which are omitted on all of the edges. So this is, it has the same information as the Cartan matrix, but you can see why this is called the monster in so many different ways. Each node in this diagram represents one block of the matrix. Now, to unravel the information that's encoded in the Dinkin diagram, let's just recall that the roots of a Lie algebra, well, they play the role of eigenvalues for the adjoint representation of the Cartan subalgebra on the rest of the Lie algebra. So here H is an element of the Cartan subalgebra, and alpha of H is the root corresponding to alpha, which is an element of the dual space of the Cartan subalgebra. Now, the simple roots are a linearly independent subset that generates the collection of all roots of the Lie algebra, and they lie on a lattice. So a choice of eigenvectors for the simple roots are called simple root vectors, and they generate the whole Lie algebra. Now, the roots of a Lie algebra, finite or infinite dimensional, can be realized geometrically in a vector space, in a real vector space in finite dimensions. In infinite dimensions, in particular in this case, we take a Lorentzian vector space, and we may take this space to be two-dimensional in the case of the monster Lie algebra. Now, if it were not for this special fact, which is due to the redundancy that's in the Cartan matrix and the Dinkin diagram, so that when we mod out by the center, it turns out that we can take this space to be two-dimensional. If it were not for this, I'm not sure if we could prove anything, but this turns out to be an advantageous property of the monster Lie algebra, and it's what allows us to progress in the way that we have. Now, for infinite dimensional Lie algebras, so we've got this Lorentzian norm in our vector space, and a root's called real if the square norm is positive, and imaginary if the square norm is less than or equal to 0. Now, in a finite dimensional Lie algebra, all the roots are real. The simple roots of a Kac-Moody algebra are real roots. Now, this is where the theory deviates even from Kac-Moody algebras. Borcherds algebras have simple imaginary roots, which are signified in the Cartan matrix by negative numbers on the diagonal. Now, we can map the roots into this two-dimensional Lorentzian space, so we can identify the root lattice of the monster Lie algebra with the Lorentzian lattice 2 subscript 1, 1, which is just the usual integer lattice with this bilinear form, which gives it a Lorentzian signature. So again, the monster Lie algebra has imaginary simple roots, and the imaginary simple roots are on this vertical line. Now, this notation is going to look very strange, and you can essentially ignore that for the time being. But on these hyperbolas, which are indicated in red, are all the imaginary roots, and they form a kind of an imaginary cone. Now, there's only one real root, that is, there's only one root of positive squared length, and it's denoted by alpha minus 1, and you can ignore the bar on the top of the roots in this diagram. Alpha minus 1, it sits on the blue hyperbola. There's one real root, which generates a copy of, it's essentially an SL2, but it turns out to be a GL2. And then there are these infinitely many imaginary roots, and in fact, infinitely many imaginary simple roots. Now, there's something called root space decomposition or Cartan decomposition of M and of Kac-Moody algebras and simple Lie algebras. It's also called triangular decomposition, where there's a Cartan subalgebra, which is finite dimensional, even in this case. And the Lie algebra breaks up in, so this is the eigenspace decomposition for the adjoint action, also called Cartan decomposition. The Lie algebra breaks up into a direct sum of the positive root spaces, eigenspaces, and the negative ones. Cartan subalgebra is finite dimensional. Now, I should have mentioned that the roots all lie on a lattice, and the coefficients are either all positive or all negative. If the coefficients are positive, we call the roots positive, and negative, we call them negative. And so, as in the diagram we just saw, the roots occur only in the first and third quadrants. Now, of course, to understand and to know this Lie algebra, we want to understand this decomposition. And it's a decomposition into a direct sum of finite dimensional spaces M sub alpha. Now, the dimensions of real root spaces, that is of eigenspaces or root spaces relative to real roots, the dimension is equal to 1. So of course, for finite dimensional simple Lie algebras, all of the root spaces are one-dimensional. For Kac-Moody algebras, the simple root spaces are one-dimensional. However, even for Kac-Moody algebras, the imaginary root spaces have dimension greater than 1. They're finite, but they do have dimension greater than 1. The same is true for Borcherds algebras and for the monster Lie algebra. Now, the dimensions of the M sub alpha for alpha imaginary, are all finite. And for the monster, they're easily determined, even though they grow exponentially. Now, this is another special property of the monster Lie algebra. And this is really what allowed it to play an important role in the proof of the monstrous Moonshine conjectures. Because knowledge of the root multiplicities or the dimensions of the imaginary root spaces allows us to construct, to write down the denominator identity from the Wildcat's character formula. Now, in many cases, and in this particular case, the denominator identities are related to automorphic forms of interest, and they have a physical interpretation, which is the case here as well. Now, the problem of determining the dimensions of imaginary root spaces is not yet solved for hyperbolic Kac-Moody algebras. The dimensions are known only by recursive formulas in every example of a hyperbolic Kac-Moody algebra. I didn't define that class of Kac-Moody algebras, but they're an important class of non-affine Kac-Moody algebras. Now, I've written the general form of the denominator identity for a symmetrizable Kac-Moody algebra. It relates the orbits of the Weil group and the root multiplicities. So just taking a look at the left-hand side and the right-hand side look very different. The left-hand side is an infinite product and the right-hand side is an infinite sum. So the left-hand side is a product over all positive roots. The multiplicity is the dimension of the root space. E here denotes a formal exponential. For infinite dimensional Lie algebras, the Weil group or the reflection group of the root system is infinite. So the right-hand side is an infinite sum. Now, if we apply this, so this denominator identity came from the character formula for the trivial one-dimensional module, which has character equal to 1. And that allows us to obtain this, this identity. Now, of course, to know what this identity is saying, we need to know all the ingredients. The simple roots determine the Weil group and hence the right-hand side of the denominator identity. The root multiplicities determine the left-hand side of the denominator identity. So we don't really know, we've got to go further in the case of hyperbolic Kac-Moody algebras to be able to write down this identity. For affine algebras, this identity gives us the well-known Jacobi triple product identity. In the case of the monster Lie algebra, the denominator identity turns out to be the famous product formula for the modular J function, proven independently by Conway-Norton and Zagier. Now, the monster Lie algebra is an example of what became known as an automorphic form correction Lie algebra. And this is what I meant, that we had to make an adjustment to Kac-Moody algebras in order to gain knowledge of their denominator identities. There's this family of so-called automorphic form correction Lie algebras, and these Lie algebras have the property that their denominator functions are automorphic forms, such as this one for the monster Lie algebra. Now, Kac-Moody algebras can be extended to automorphic form correction Lie algebras. I won't go into that today, but such Lie algebras have been studied by Kim and Lee, Gritsenko and Nikulin. Now, just to put a different spin on the importance of the monster Lie algebra, its appearance in other Borcherds algebras as symmetries in string theory have been noted since the 1990s, particularly for the heterotic string, initially by Harvey and Moore, and more recently by Paquette, Persson, and Volpato. I'm very interested in the construction, and I have some work in progress with Natalie Paquette to say something about the discrete symmetries of the heterotic string. Now, thanks for your patience during that somewhat lengthy introduction. Let's get back to the main question to find a Lie group analog for the monster Lie algebra. As we mentioned, there are many methods for associating Lie group analogs to Cat-Moody algebras. The monster Lie algebra describes physical symmetry, so it's important to associate a group, which would be an analog of a Lie group. And in particular, this would give us a global symmetry structure, which we'd like to interpret as a group of transformations, which are automorphisms of the Lie algebra, ideally, because this is the relationship that we have in finite dimensions and also for Cat-Moody algebras. Now, as I have become interested in applications to physics, I've noticed that many applications for constructing automorphisms of infinite dimensional Lie algebras in physics involve exponentiating the adjoint representation only when it's defined, because it's not defined everywhere. And this is one of the problems we face in infinite dimensions. It's defined on the so-called locally finite elements, that is on real roots, but in general, not their linear combinations. This provides only a fractured picture of symmetry, and it turns out not to be ideal for applications. On the other hand, of course, we can understand why we're led to down this road when we're studying applications, because many of the methods for associating Lie groups to finite dimensional simple Lie algebras and Cat-Moody algebras break down for Borcherds algebras. Perhaps I'll pause briefly and just see if there are any questions before we go on.
Sorry, I had one question. So
Yes.
how much of this sort of extends to, other sporadic groups?
So that's a really good question, and I would say that I'm starting to learn about vertex operator algebras for other sporadic simple groups, and certainly one could ask about an analog of the monster Lie algebra for other sporadic simple groups as well. So there are probably things I don't know because I'm a newcomer to the subject. There's certainly something called a baby monster Lie algebra. Yeah, there's a baby monster Lie algebra, which I guess there's a baby monster sporadic group.
Yes.
So
Second biggest one.
Yeah, the second biggest one. And there are other vertex operator algebras for certainly for the Conway group and the Mathieu group. I'm not sure if there are Lie algebras in that case, but as I said, I'm a newcomer. So in general, our methods will apply to all of those.
Great.
And certainly we thought we could do something for the baby monster as well. So so we hope we can extend the results that we have.
Okay, thank you.
Now let's just review the relationship between the exponential map and adjoint representation. If we have a simple Lie algebra and its corresponding simple Lie group or linear algebraic group, there's a formal exponential, as we mentioned already, that takes us from the Lie group, Lie algebra to the Lie group. Now, of course, everything's completely well-defined in finite dimensions, and that's because the exponential is a finite terminating series, because you can't keep applying the adjoint map and getting longer and longer commutators. So there's a limit on the growth of commutators in finite dimensions, and so the exponential map is a finite terminating series. So if we applied exp to the adjoint map, we'd get something, and applied it to an element of the Lie algebra, we'd get something of the form y plus bracket xy, and so on and so on. So these brackets are terminating and in finite dimensions, and thus exp of add is a well-defined element of the automorphism group of a simple Lie algebra. So we can use this fact to generate a group of automorphisms of the following type. So these are known as Chevalley groups. And we can take a group generated by elements of the form exp_add of simple root vectors. So alpha here, actually, we don't have to restrict to the simple ones. Alpha here is any root. There are finitely many roots. Exp_add is a well-defined automorphism of the Lie algebra. We do assume that we have a Chevalley basis, which is a basis for the Lie algebra whose structure constants are integral and behaves nicely with respect to a Chevalley or Cartan involution. So these generators of the group are finite sums when applied to any element of the Lie algebra, and hence they're well-defined elements of the automorphism group. Now, this is a group that's associated to the Lie algebra. It's well, it looks different at the outset to the matrix groups. Of course, there's a relationship between them, but this group can now be given in terms of generators and defining relations, which were worked out by Steinberg. And when we take the image of the group generated in this way, in the automorphism group of the Lie algebra, we obtain what's called a Chevalley group of adjoint type. Now, when we consider this picture for infinite dimensional Lie algebras, well, of course, the setting's very different, but certain things do carry over. In particular, a similar method works for constructing adjoint groups for Kac-Moody algebras. And that's because the adjoint representation of a Kac-Moody algebra is what we call locally nilpotent on the simple root vectors. That is, the adjoint is terminated. So if we apply it to simple root vectors, or in fact any real root vectors, we only need the simple ones because they generate the whole Lie algebra. When we apply add of a simple root vector to an element of the Lie algebra, again, there's a bound on the length of commutators. And so these brackets are eventually vanishing for the simple root vectors. And so once again, because of the bound on the length of commutators, exp_add of EI, exp_add of FI, where EI and FI are the simple root vectors. So these are finite sums when applied to an element of the Lie algebra, and hence they're well-defined elements of the automorphism group of a Kac-Moody algebra. So once again, we can consider the group generated by exp_add of EI, exp_add of FI, and of course we can put in parameters from the underlying field. Now, adjoint constructions of Kac-Moody groups are well known. There's also a notion of a simply connected Chevalley group for both finite dimensional and Kac-Moody algebras, where the adjoint representation is replaced by an integrable highest weight representation. And that's a representation that in particular is locally nilpotent on simple root vectors for Kac-Moody algebras. Okay, so this is the reason why there's an established theory of groups for Kac-Moody algebras, but this approach no longer works for Borcherds algebras. So exp_add for Borcherds algebras, it turns out the adjoint representation is not locally nilpotent. So this series, exp_add, even if we take the real, there's only one real root vector, one real root. If we take a root vector relative to the real root, of course, this is a finite sum. But we mentioned that the Monster Lie algebra has infinitely many imaginary simple roots. So this is generally an infinite sum, not a well-defined automorphism, and so we need a different approach. Now, because we're mathematicians, we wanted automorphisms of the Lie algebra. Of course, if you didn't care about automorphisms, you could generate some sort of a group this way. But what's really natural is to be able to relate the group back to the Lie algebra, and that's what we wanted to do. Now, there is another approach. We can consider groups generated by, defined by generators and relations. And in the finite dimensional case, Steinberg gave a defining presentation for finite dimensional Chevalley groups over commutative rings, both in the adjoint and simply connected case. Now, Tietz also gave generators and relations for Cass-Moody groups, generalizing Steinberg's presentation. And these presentations by Steinberg and Tietz can be realized as groups of automorphisms of the underlying Lie algebras. Once we identify the generators with elements of the form x add of x for a suitable choice of x. Now, one drawback is that Tietz's presentation does not contain explicit generators corresponding to imaginary roots. Another problem with Tietz's presentation for Cass-Moody algebras is that it's a kind of abstract presentation, and it turns out that you've got to carry out a procedure to determine the relations, and it's right on the boundary of what's computationally feasible. So it's not an explicit presentation for Cass-Moody algebras. But we can kind of mimic Steinberg and Tietz's presentations for the monster Lie algebra by kind of formally integrating the defining relations of the Lie algebra. Now, this is actually the first group that we discovered, if you like. The problem with this approach is that the group cannot naturally be interpreted in terms of automorphisms of the monster Lie algebra. Now, in order to explain how we really got around all these problems with the monster, let's just recall something about summability and infinite sums. So again, it's about the relationship between the exponential map and the adjoint representation. So we've seen this expression, exp of add applied to, exp of add of x applied to an element of a Lie algebra. We get this infinite sum. Now, we can always consider this formally, the formal exponential, without consideration of convergence. We can just consider this as an infinite sum. Now, when x is a simple root vector of a finite dimensional semi-simple or Cass-Moody algebra, these sums actually are finite. And so they're well-defined automorphisms. And such a finite expression is called summable. And this is now language we've borrowed from vertex operator algebras. An infinite sum of operators is called summable if it reduces to a finite sum when it's applied to any element of the Lie algebra. So this infinite sum, when applied to y, reduces to a finite sum. Now, unfortunately for imaginary simple root vectors of the monster Lie algebra, x add of EI is not summable when applied to any vector of the monster Lie algebra. Okay, so we're stuck with infinite sums. So I keep saying we, and I have not mentioned the collaborators for this project. So Scott Murray is one of my collaborators, Elizabeth Jurisich, Abid Ali, and Scott and Abid, I think, are here today. Elizabeth Jurisich is head of department at College of Charleston, and she was going to try to make it, but I think she's stuck in a meeting. Okay, so being stuck with infinite sums for the monster Lie algebra, what we decided to do was build an ambient structure where these infinite sums would make sense. So one idea we had, which was which was used by Kumar for Cass-Moody algebras and for Rousseau, was to take a positive formal completion. That is, to take the Cartan or root space decomposition and take a formal completion in the positive direction. That is, we replace the infinite direct sum of positive root spaces by the infinite direct product. Now, it turns out that, as we mentioned, the root spaces are all finite dimensional. And it turns out that we can, in a compatible way, write this product over the natural numbers instead of the root lattice. So when we take this positive formal completion, it's naturally a pro-nilpotent Lie algebra. That is an inverse limit of finite dimensional Lie algebras. So we can construct this family of ideals such that Ni hat, such that each of these quotients are finite dimensional, and the positive formal completion is an inverse limit or projective limit of these finite dimensional Lie algebras. Now, an element of, so we can then form M hat, which is, we've just replaced n plus by n hat plus. And when we take an element of the completion of the monster Lie algebra with a hat on top of it, an element's an infinite formal sum. Now, this is not a new idea. As I mentioned, it was used by Rousseau and Kumar for Cass-Moody algebras, but it was also used by John von Neumann, who wrote a monograph about this idea in 1939. It's called On Infinite Direct Products. He was mainly concerned with absolute convergence. Now, we're actually in a formal setting here. So we want to somehow get around the idea of convergence. We're not going to get convergence, and we don't have the analytic structure to be able to talk about convergence. I mean, it would be ideal, because after all, that's how you handle things for vertex operator algebras. But at the moment, we don't have the analytic tools, so we're going to work in the formal setting. Now, of course, applications, many of them require absolute convergence or take truncations at some finite level. Now, we're going to work formally in the absence of, without assumptions of convergence, in the absence of analytic structure. But we don't want to take truncations at a finite level, because a truncation will, so when you truncate, you're throwing away information, and we want to get a global picture here. Now, generalizing the notion of summability, we can say that X add of EI applied to Y is pro-summable for an element Y of the completed monster Lie algebra, because there's this remarkable property of X add for the monster Lie algebra. If we take a projection onto n minus direct sum H, direct sum this finite dimensional piece, the n hat plus mod ni hat, all of them are finite dimensional. X add of EI applied to Y turns out to be a finite sum, albeit of unbounded length, for each natural number I. Okay, so this is, again, borrowing ideas from vertex operator algebras. This means that X add of EI is a finite sum when projected to the finite dimensional homogeneous components of M hat. And this will allow us to construct pro-summable groups of automorphisms of the completion. Now, if I can, oops. Okay, there's the finite sum. Thanks to Scott Murray for computing that finite piece. So if we look at these finite pieces in the grading of the completed Lie algebra, it turns out that X bad is a finite sum on the nose. So it's finite when restricted to these finite dimensional graded components. And so it makes sense from the point of view of infinite sums of operators in vertex operator algebra theory. It's finite on finite dimensional components, so it's well defined. Now, just to give a summary of the main results. So in joint work with Elizabeth Jurisich and Scott Murray, we've constructed a complete pro-unipotent adjoint group of automorphisms of the completion. Now, it turns out here that we only In this description, we only used generators from the n hat plus, the positive part of the completed Lie algebra. This gives us an inverse limit of finite dimensional unipotent groups corresponding to simple roots in the positive direction. The generators of this group as a topological group are a power series with constant term equal to 1. Elements of the group are of the form, and we get an infinite product of exponentials. When you expand them out, they still have constant term 1. An element of the Lie algebra is an infinite formal sum, but when we apply elements of the group U hat elements of the group to elements of the Lie algebra, we get finite sums when restricted to any component, any greater component of the completed Lie algebra. So as I mentioned, for Kac-Moody algebras, complete pro-unipotent groups have been constructed by Kumar and Russo. We couldn't exactly use their methods because Kumar's construction was algebro-geometric, and we don't have a geometry here. Russo's construction was functorial and was not explicit. We wanted explicit descriptions of groups of automorphisms in our setting. And in joint work with Abid Ali, we've extended this construction to all Borcherds algebras that have a symmetric generalized Cartan matrix. Now, actually before this pro-unipotent group, we had constructed a Lie group analog for the monster Lie algebra, not its completion. We constructed a group given by generators and relations. And our group does contain generators associated with imaginary roots and the relations between them. This group by generators and relations is generated by GL2 subgroups, just as Kac-Moody groups and Chevalley groups are generated by SL2s. In our case, we have GL2 subgroups associated to both real and imaginary roots. And the defining relations were determined from the Lie algebra relations by looking at interacting GL2 subalgebras, which generate the monster, and by a kind of process of formal integration. Now, this group has a subgroup corresponding to positive imaginary roots. And it turns out that this group embeds in our pro-unipotent complete group of automorphisms of M hat. So the group given by generators and relations is not a group of automorphisms, but it contains a subgroup of automorphisms of M hat. That shows us that we're on the right track with this group given by generators and relations. Now, provided I have time, I'll briefly mention an application to discrete symmetries in the heterotic string. Now, I mentioned that Paquet, Persson, and Volpato proposed a physical interpretation of a generalized version of the Monstrous Moonshine conjecture in terms of the E8 times E8 heterotic string. Now, in joint work with Natalie Paquet, we have an interpretation of discrete symmetries of the root system of the monster Lie algebra. And actually, there's a more general family of monstrous Lie algebras constructed by Carnahan, one for each element of the monster finite simple group. So we can interpret these in terms of discrete symmetries of the heterotic string. And their model is compactified to 1+1 dimensions, and the type of compactification is related to the Moonshine module of Frenkel, Lepowski, and Merman. Look, I'll skip this thing about supersymmetric indices and BPS states because that's a bit of a longer story. Now, what's nice to see is that following on from joint work with Hong Chan, Elizabeth Jurisich, and Scott Murray, and Hong Chan's a graduate student at Rutgers. So in this work, we showed that an imaginary reflection That is, there is a candidate for a reflection with respect to an imaginary simple root. So this leads to the following relationship between discrete symmetries of the compactified heterotic string and discrete symmetries of the monstrous Lie algebras. So the Cartan involution, which exchanges positive and negative root spaces in the monster Lie algebra, was shown by Paquet, Persson, and Volpato to be a sign change in left-moving moment in the vertex operators corresponding to left-moving momentum. We showed in our paper that it was a product of the vulgar reflection corresponding to the real root and this imaginary reflection. And then we showed with Natalie Paquet that this can be interpreted in terms of a product of a time reversal symmetry and a parity transformation. So the time reversal symmetry is a sign change in the time coordinate of the compactified string. The parity transformation changes the sign of momentum and winding of closed strings in the spatial direction. Just to finish off, this is a new subject and there are a lot of different questions, as well as Dan's excellent question about other sporadic groups. It turns out that our methods can also be applied to group constructions for hyperbolic Hess-Moody algebras. This gives an explicit method for associating root groups and their generators to imaginary roots of hyperbolic Hess-Moody algebras. So this has only been seen in a functorial way by Rousseau and Timothy Marquis. We hope to generate a very explicit and concrete theory here. We're also studying a larger group associated to the complete monster Lie algebra by considering the group generated by our U-hat, which was the complete pro-unipotent group, a Toral subgroup, which is just the exponential of the finite dimensional Cartan subalgebra, and a group U minus, which is generated by the negative real simple roots. So this would be the analog of a complete Hess-Moody group for the monster Lie algebra. It's tricky because you're kind of combining an infinite dimensional group with these finite dimensional ones. And it's very delicate to see how they interact. Also, the way we approach the question, our group constructions don't reflect the action of the monster finite simple group on the vertex operator algebra V natural. We're trying to take a different approach through vertex operator algebras to relate our Lie group construction to the monster finite simple group and its action on V natural. Also, there's a discrete subgroup of our group given by generators and relations. It's an analog of SL2 of Z. We're trying to determine the relationship between this group and the monster finite simple group, and in addition to integral forms of the vertex operator algebra V natural. I also very much like the question that Dan asked. You could easily add his question to this list of future directions where we look at other sporadic simple groups, but our methods are very general. Although it does depend on, our methods do depend on a decomposition of the Lie algebra, of the monster Lie algebra, proven by Elizabeth Jurisich in her PhD thesis, that M decomposes as a direct sum of a GL2 and two infinite free Lie algebras. But there is a class of Hess-Moody algebras, and I think this could also be applied to the Conway group in some way, but it's also, we can prove that it's true for the baby monster Lie algebra as well. So anyway, thank you so much for your attention. And it's a pleasure to address this audience, and thanks so much.
Let us thank Lisa. Are there any questions?
Yeah, can I ask one more?
Yes, please.
So, does it make sense? I mean, maybe I missed this part, but does it make sense to take your group and then differentiate to get a Lie algebra? And what Lie algebra do you actually get? Do you get the monster Lie algebra back again, or?
Yes, I didn't say much about it, but so it turns out that there is actually a formal derivative. We don't see it rigorously until we go to the completion.
Okay.
But before we had that complete structure, we kind of pretended that it existed.
Mhm.
And we rewrote we started with the monster Lie algebra. We rewrote the defining relations in a certain form, which would be more amenable to getting something like a Kac-Moody group. And then we kind of tried to guess what a formal integration of those relations would be. And so we proposed a set of group relations, which if you differentiate them using the rigorous formal exponential, you do get exactly the unipotent part of the monster Lie algebra.
Good. Thanks.
Are there other questions? Okay, if not, let's thank Lisa again.